for material science and engineering. Julia started here at Cornell in 2019, so she's been here for a little bit now. Before that was at the University of Michigan, and before that ETH in Zurich. So Julia's going to be telling us about soft matter and crystalline structures and self-assembly. Julia, take it away.
Thank you so much. You hear me, everyone? Okay, that's good. I'm really thrilled to be here and to make more connections within Cornell. I'm not really new to campus anymore. Those of you who I've had lunch with probably know that I've spent more time here within COVID than out of COVID, so that's how I measure that I'm still relatively new. I don't know that many lower faces yet. But I'm really thrilled to talk to you all with Mesoscale today. My background is in physics, and I'm really very much a material scientist, which you'll know if I throw all those crystalline structures at you. That's kind of, when you see space groups, you know that you're in a material science department. I'll probably not show too many of those space groups, but the structures nonetheless. So my background is actually in hard condensed matter experiments. I will only be talking about soft condensed matter simulations now. And the interesting connector I'll talk about on like slide 2 approximately. Really, my beginning pitch is usually just, we want our materials to be more and more functional. Often that means that they become more and more complex so that we can graduate from this one all the way over here. And ideally, we want to be able to design for those functionalities, build those complex materials in a dedicated manner. So we have to understand how they form. And that's something that we don't really know yet how it works. And I learned that in my PhD when I found out that you have intermetallic structures that are not like your usual metals, just sphere packings, and that's all. But you actually have metals, if you just put 2 or 3 elements together, that have unit cells with hundreds and thousands of atoms, which makes no intuitive sense. Chemists can compute their properties, but you don't really know why that happens. And about 15 years ago, the same started happening with soft condensed matter, where for a long time, really simple building blocks were found to form really simple structures, sphere packings, just like in metals. People started discovering more and more complicated structures. So they found, for example, that these colloids here form like basalt structures, still relatively simple. But then dendrimers formed this beautiful A15 structure type, or whatever you want to call it, if you're into that. Polymers, nanoparticles, surfactants, and so on. So all of these form crystal structure types that we actually know from the atomic scale, and that's what drew me into this field where I see the same crystal structures, we're on a completely different length scale, completely different interactions, and we still, just like in many metals, don't really understand why they form. So the nomenclature that I'm using for crystal structure types really leans onto that parallel of where are the particles in the unit cell, irrespective of what the particles are. So they are called Pearson symbols, and they consist of the Bravais letters. There are 14 of those, right? This one is cubic primitive, tetrahedral primitive, and so on, and the number of particles per unit cell. So when I say complex structures, that's the way to measure how truthful I am, what I mean by complex. So this one may be not too complex with just two particles per unit cell. Here you have 30, that's already a little bit more complicated. And then you have the structure type, the prototypical structure. So all of these are actually, well, this is not quite metallic in the sense of a property, but all of these are composed mostly of metallic elements, which means you're seeing this entire dibloco polymer micelle sit on a position in the unit cell where typically a chromium or an iron atom would sit. So all these soft matter scientists start finding these crystal structures that they're not super familiar with because they never had to deal with that kind of complexity. And that's where my happy place really is. So that's where I started diving into that field, coming from something rather different originally. So the kinds of models that I'm going to show you today, I'm just going to talk about simulations and from time to time show you here, we're not just making this up, sometimes this is being seen in experiments too. I'm going to show you 2 types of models. Anisotropic hard particles, so faceted shapes most often, and isotropic attractive particles, which I typically call squishy spheres. They are both simulated with different types of simulations, Monte Carlo in the case of hard particles, and molecular dynamics in the case of the isotropic interacting particles. And I want to show you how, you can see a lot of different structural phenomena in these hard particle systems that you might not have expected. Hopefully, will not have expected, so I can surprise you. A little bit of our study, one of our studies that goes into the differences or not between bulk and small confined structures. And then on the isotropic particle side, I'll show you some really cool new crystal structures where I, as a crystallographer, my heart starts beating a little faster than we found. How we try to study growth and really how this assembly process occurs, and what happens if you don't just have one type of particle size, but things become more complicated. That's typically what experimentalists ask me. Well, what happens if you don't have a perfect batch of particles, but you have different sizes? We're trying to approximate what happens without breaking the computer. So I'm starting with hard faceted shapes. And if we take one step back and we don't do facets, but we just do hard shapes, ideally spheres, which are nice and simple. You all know this way better than me. Their densest packing was hundreds of years ago postulated to be any stacking variation, but basically this densest sphere packing. And then at some point it was even proven, which is wonderful. But, and if you have actual spheres and you put them in a box and you shake the box, they will actually want to pack like that. Now, with some faceted shapes, with some anisotropic shapes, you also come up with a structure that's relatively simple and intuitive, and if you have cubes and you put them in a box and shake them, they will still assemble this kind of structure. And that happens on the nanoscale too. Well, here you're probably not really shaking them, but these nanoscale nanoparticles will also assemble nicely, facet to facet, into this simple structure. However, this is just the start, right? There are all kinds of other shapes, and you might wonder, well, what happens if I put these guys here into a box and shake it, and wait, what happens? So more than 10 years ago, my postdoc advisor and her students were like, well, let's take the simplest one of this bunch and see what happens. So they took the tetrahedron, put it in a box, and took it, well, computationally, and wanted to see what structure comes out. And that's where hard particle Monte Carlo simulations come in. The same type that we're conducting now, only back then they had to invent the wheel or whatever. They had to come up with the code from scratch. Really, all that we're doing is the interactions between these shapes are purely volume exclusion. So if they were floating toward each other and they would, in the next step, possibly overlap, that move is rejected. If they don't overlap, if one of them moves around, that move is accepted. And the same goes for rotations. They can't overlap is really the only rule. So if you put them into a large box and let them float around, they're just going to bounce off of each other and not do anything super exciting for a crystallographer. But if you crowd them together, you shrink your box, you force them close together, you'll see that they crystallize just like attractive particles would. So these are octahedra. When they're blue, they're still in fluid phase, and then do this again. They are colored yellow as soon as they're part of the crystal. So this is really the moment nucleation takes over and the entire system crystallizes.
Sorry, are there any forces acting on them, or is it purely random perturbations?
It's purely random perturbations. It's really there's no enthalpy. There are no enthalpic forces, no explicit interactions. Basically, they are ordering due to entropy, due to configurational entropy. So there's not, this system doesn't even have temperature. Or, no. Yes.
The particle coloring is just you're calculating some order parameter?
Yes, exactly. It's just a simple order parameter applied that figures out whether you end up. It's going to actually be a persistent problem, which order parameters to apply. I'm not even sure which one they applied here, but it's probably one of them. Like it's an older video. It's probably one of the more basic ones that's just supposed to distinguish between fluid and solid. So that looks at the local symmetry. But we've since then employed more complicated order parameters too, so that we can actually distinguish different crystal structures from each other from where they crystallize. But here, the simple one did the trick just to distinguish the fluid from the solid.
So, since we have interrupted you, let me ask another one.
Of course.
In the previous slide, you showed us an imperfect, well, I guess 2 slides ago. Yeah, no. The real materials. So there were some small defects. Are they important in the story you're going to tell us, or we're not interested in defects at all?
So I'm not going to talk almost at all about cubes, and that's why they're not so important. They're about as important as they are in a random, like in most materials. In cubes, they're very important because of how well the cubic, like the columns of the sheets can move against one another. There are actually specific studies that just study cubes and the defect behavior because it's very non-typical, and I cannot tell you more about it than that because I didn't actually study them in that much detail. But with cubes are special. With their defects, most of the others are just like any old material. From time to time, you have a point defect, you have a dislocation. They look, honestly, they behave differently from atomic defects probably because shape is involved, just like surfaces will behave differently. But yeah, it's not going to play a big role. This was not supposed to be like sending you an early message of like but yeah, it's a good question though, because actually one of the messages that I'm sending you here early on is actually very similar things happen on this scale in these systems that do in other crystals. Defects will be one of them. All right. So Monte Carlo simulations, and I told you the first one that they wanted to look at was the tetrahedron, the simplest one, presumably, and what they found was that tetrahedra, hard tetrahedra, form a dodecahedral quasicrystal. Who knows what a quasicrystal is? That's beautiful. I don't have a quasicrystal intro slide, but I will talk about them for a minute, and please ask questions if you want to. Crystals are really just made up of unit cells that are periodic and usually in 3 dimensions. So you have one unit cell that you can describe with symmetry and all of that, and then you just need 3 vectors to tile 3-dimensional space, and you have your crystal, your periodic crystal. Quasicrystals are aperiodic. They're not non-periodic, so they're not quasi-crystals, but they're fully periodic in a higher dimensional space. You all would probably appreciate that more than I do. So your unit cell is not actually 3-dimensional, but typically 5 or 6-dimensional. And you project it down to 3 dimensions, you have something not actually periodic in 3D, but it still produces a diffraction pattern that is discrete. So it's still fully ordered. You have still very discrete typical distances, only they never, like they repeat, but they don't repeat in a periodic pattern in 3 dimensions. They're complicated structures, but they're beautiful and they're ordered, and we don't really understand why they appear. They also appear in metals, actually. Maybe not too coincidentally. So the other important feature of quasicrystals is that they have non-crystallographic symmetries. So crystals in 3 dimensions can have 1, 2, 3, 4, 6-fold symmetries, hexagonal and tetragonal and cubic and so on. Symmetries, but here you have a 12-fold symmetry, which is not congruent with 3-dimensional grids. So basically what they saw was they see this they're just randomly colored. You see this pattern which doesn't really look disordered, but it also doesn't really look periodic. And if you compute the Fourier transform, you see that you have a 12-fold diffraction pattern. This is a little misleading. These heart shape interactions are actually very weak, so you would never see something so beautiful and sharp from something so small. But if you run a really big system and you quench it hard enough, you'll actually be able to disentangle the diffraction properly. So they could tell it's quasicrystalline, it's ordered, it's just not ordered or not periodic in 3 dimensions. It actually maps to a triangle square tiling that's also aperiodic. So the quasicrystal researchers that have been dealing with metals for a while, they came into the field through essentially these kinds of studies where suddenly in soft matter and in these coarse-grained simulations where they didn't expect to see anything super complicated, they started seeing quasicrystals. This is approximately what the motifs look like if you color the tetrahedra accordingly. So you have these columns here of little pentagonal-like pyramids, hexagonal, like rings of dimers, and then they kind of pattern these triangles and squares in this tiling to form this really complicated structure. And that's just the simplest shape, right? I was going to move on unless you wanted to talk more about the quadricrystals. I want to break your brains, but yes.
I was just wondering, when you say that you have periodic in higher dimensions, so is it just that the structure, you cannot show that it's embeddable in a 3-dimensional space? Is that what you
We can't show that it's what in 3-dimensional space?
Embeddable? Something like that? I'm just wondering what those higher dimensions are.
They're honestly, you all probably understand them better than I do. We call them perpendicular space, and essentially it means that your atoms, if this was an atomic structure, your particle positions are not points anymore, but if you have a five-dimensional, like this would probably be a five-dimensional model that you would need with your atomic domains or particle domains to being two-dimensional entities, and you have to like cut and project them down to 3 dimensions. It's called actually embedding, so you're already using the lingo that the quasi-crystal people are using. But yeah, basically you can't describe it through something that's 3D-dimensional, but I'm not sure that that's part of answering your question. Okay, cool. Okay, I'm not going to talk much about quasi-crystals, which is why I didn't bring you a quasi-crystal primer, apart from my words. Basically, they then went on, we're like, we can do this with all the shapes, and did 145 different tetrahedra, and it turns out not all of them are quite as crazy as tetrahedra. Tetrahedra are kind of the pinnacle of complexity, I would say, and a bunch of them are quite boring and disordered. Several are liquid crystals, so they're orientationally ordered, but not positionally ordered. Some are plastic crystals, so positionally ordered, but not orientationally ordered. And then down here you have proper assortment of nice crystal structures that are just formed by their different particle shapes. And, okay, those are the things that I said. The tetrahedron is right here, and there are also other structure types that now that you know the Pearson symbol, you'll be able to read, right? This is the basic cubic packing or the cubic closed packing. This is BCC. This is one of the structure types that I showed you early on from the polymer micelles. This is a very typical, rather complex metal. This is gamma brass, and the sigma phase. So a bunch of different crystal structures, again, known from metals. Other fun phenomena are, for example, that if you mix those shapes together, and you do it wisely, so you have a really big shape and a really small shape, and you mix them together, actually what's going to happen is phase separation, and it's not very exciting. If you mix them together and they're as similar in volume as tetrahedra and octahedra, you can observe the formation of compounds. So you have your quasi-crystal over here, your boring octahedral crystal, I think there's hexagonal symmetry, I actually am not sure anymore, over there, and in between you have a nice compound crystal structure with a completely different symmetry. So they want to form a structure together that is otherwise not observed. So you see all kinds of structures, you see multi-component systems that form their own crystal structures. You can start doing things like shaving off vertices and set up a continuous phase space similar to, for example, changing position in an atomic system. You can see orientational disorder. You might have seen that I alluded to that in the plastic crystals. And we also see phase transitions, phase transformations. If we, for example, increase the pressure on our polyhedra, or if we change the shape a little bit, if we treat it as a parameter, or if you assume that, for example, have a particle that you can selectively have swell instead of changing shape, you can have the system undergo a phase transition. This one here is interesting because it starts with diamond, which is kind of interesting for photonic applications because of its band gap, and then you can force a transition to a lower symmetry structure that would have a different band gap, so you would have different photonic properties. So all those things exist in heart-shaped systems without any explicit interactions at all.
How do you know that you shook it long enough? How do you know that something is truly disordered? Maybe you didn't have enough of them, or...
It's entirely possible, especially for this study, right? Because that was still relatively early in the hard anisotropic shape realm, I'd say. I personally assume if you simulated some of these again and for longer, you might find some order. As I said, the directions are really weak, so actually it's really hard to discern order even if it's there. Yeah, I don't have a better answer than we're actually not 100% sure. So there is one paper out there actually that's looking, and I'll show you that in a sec. There is this phase space that Rachel is looking at has a disordered region, and I'll talk about it now, where basically you have competing motifs, and between one motif forming one structure and the other motif forming the other structure, you have a disordered region where actually glassy behavior has been observed, and for this very specific system, they have kind of proven it to that degree. But for the whole breadth of those shapes that I showed, we haven't had such deep studies for each of them.
I've got a question.
Absolutely.
I guess there are kind of fancy Monte Carlo moves that are used in, like, for heart sphere. Monte Carlo, thinking of the stuff Werner and Cross have done. Is there anything like that in these more complicated shapes, or does the geometry just sort of make those more exotic kind of moves very difficult?
Do you mean fancy in the sense of
Sort
like
of-
swapping moves? And
Yeah,
stuff like that?
multiple sort of coordinated motions.
There are none of those are happening here. So those are all, basically, I think one of the ideas is really to stick with the self-assembly theme. So to really say, okay, if we make our steps short enough, we could really interpret those as trajectories. Like, of course, there's no time, these are no real trajectories, but we could interpret them as such because we don't have swap moves or anything like that. I know that in the community there are a bunch of people who actually are using swap moves depending on what kinds of systems they investigate, just because otherwise they would be arrested rather than form anything. But these form without swap moves, or like the rigid, what you said, like if you have like a collective move.
They're like whole chains of things
Yeah.
that move together and stuff.
No, this is way less fancy.
Okay.
Yeah, the simulations are really the most, I think I said this exact thing earlier for lunch, so excuse me, but it's the most pedestrian thing of what we do. These are very out of the box or whatever. Simulations, the software is open source, you can try it, it's very fun actually to use. My undergrads can use it because it has a Python wrapper around the C++ CUDA core, it runs on GPUs. If you run, at least the molecular dynamics simulations run well on GPUs, the Monte Carlo can run on GPUs, but it's still more efficient. That's a whole different story. Okay, so in the anisotropic shapes, is this correct? This is correct.
Yeah.
Okay, well, we'll skip something. In the shape space, we have currently one project that looks at shapes at confinement, and Rachel is leading it. And basically, our inspiration came from two sides. One is the one with hard shapes that are anisotropic, make fun structures. The other one is the one with spheres. So spheres, hard spheres, were found to form, they form FCC. They form the simple cubic closed packing. But if you form them in a very small system, they actually form this twinned arrangement. So this is an isohedral twin of these densely packed domains. So locally the structure is still the same, but you have these big twins so that you don't have like something completely pointy and anisotropic actually. And at around 100,000 particles is when they start forming single crystalline assemblies. So actually pretty large numbers. And we were wondering what the system size will do to our other types of shapes. So Rachel is doing similar simulations, but in tetrahedral systems. And that's the phase space that I was alluding to, where you have truncated tetrahedra up here, all the way to octahedra down here, and Archimedean truncated tetrahedra are somewhere here, so that's like the Archimedean shape. And tetrahedra themselves form this quasicrystal that I mentioned. And basically, the tetrahedra have this overwhelming motif of a misalignment of what we measure to be around 70.5%. So that's transferring the orientation of one of the tetrahedra to the neighboring one with like the minimum angle that's a 70-degree rotation. Whereas these Archimedean truncated tetrahedra form a diamond-type crystal structure, where this other misalignment of 90 degrees is prevalent. So it's not with a mirror, but with an inversion point, or that's how they relate to one another. In between, you have this ordered range, so that's what I meant with the motifs are competing and frustrated and forming lots. So that's the range that Rachel started investigating, and basically where before we were just shrinking our blocks with periodic boundary conditions and waiting for crystallization to happen. What we do now is we have a sort of container that we're shrinking, and we're waiting for them to arrange in some kind of pattern. And we do that, the structure depends on the system size, because the curvature of your bubble, of your container, shrinks the smaller your system is. And we simulated several replicas to be sure to properly sample the phase space, right? Because at some point they get just jammed in where they are and nothing happens anymore. Okay, so the most common motifs, again, looking at this misalignment that I just mentioned, are these 90-degree misaligned or anti-aligned truncated tetrahedra, and aligned ones here. I'm showing it to you for, can you actually see the shading? Here, where you see that here the triangles and the hexagons are aligned, and here the triangles are on top of each other. And we're projecting this this histogram onto a one-dimensional heat map so that we can look at what happens with system size. So these are tetrahedra, Archimedean tetrahedra, and the one shape in between is intermediate shape. They're actually space-filling shapes, although that's not the structure that we self-assemble into. So for tetrahedra, you see something like a lot happens around 20, so it's a relatively small system size, it's a little noisy, but then the main motif just persists and sticks around. For the space-filling truncation, you see a little bit of stuff happening here where they seem a little confused, but honestly, nothing much happens. For the Archimedean truncated tetrahedra, you see that the anti-aligned motif increases in prevalence, right? In the beginning, it's actually not the most common motif. It increases in prevalence, but even at 3,000, and now we have also measured 5,000 and 10,000 particle systems, it doesn't get that close to what the bulk looks like. So the curvature still has a huge influence on what the particles assemble as, and that I will show you an example of what they look like, and you'll see where that comes from. So basically, this is what the bulk looks like. In the bulk, you have these flat layers of anti-aligned tetrahedra, whereas in the spherical container, you have this curved layer. And as you go in layer by layer, not only are they slightly incremental with respect to one another, because each layer has more curvature and is smaller, at some point in the middle, the curvature is so high they can't form that layer at all. So that's why, even at relatively large system sizes, you won't get to the bulk confinement, to the bulk configuration. And the extreme case that we wanted to measure is what happens if you have like an infinitely large sphere. And of course we cannot simulate that, but what we can simulate is confinement between flat walls. And you end up seeing that then, of course, it's beautiful. It almost looks better than it does for just a bulk, because now you're giving it a template. The structure happens to have flat layers, and now you're really letting the flat layer align with one of the walls. However, that's where we also saw something fun for the space-filling truncated tetrahedron, where suddenly we're switching that one from its preferred misalignment to this other one because we're templating those flat layers for the walls. So we can actually tune, depending on the confinement, what kind of structure is going to form. We're wrapping up that story now, where really we're trying to emphasize, I feel like some of those things are very logical and very, very, very intuitive, but we're trying to make this into a story about how you can create a specific structure depending on how you structure its environment. Okay, so those were our anisotropic polyhedra, and we have less than half an hour for our squishy spheres. But that's really the one that I spent my postdoc with. So I'm hoping that you'll see some new fun things here as well. So now we can perform molecular dynamic simulations. Our particles are explicitly attractive, and they form way nicer crystals. And we see a few new crystal structures, and I already told you what else we're going to do. So these are the interaction potentials with which our particles interact now. They look kind of made up, but actually the oscillating pair potential is being relatively frequently used in systems, like in dynamic studies of metals. People often measure mechanical properties like this. They use empirically fitted potentials to say, okay, this mimics the aluminum, copper, or whatever interaction, and they're using this as the functional form of their interactions of hard matter systems. The Lennard-Jones-Gauss potential is really just the Lennard-Jones potential with an attractive Gaussian on top of it, where you can tune the position of the Gaussian and its relative depth with respect to the Lennard-Jones well. Both of those have usually two wells, and you can tune their positions and depths. So that's what we were going for, because then we can see how do those particles then form different crystal structures depending on what the features of the potential are. So they're isotropic, they're relatively short range, so we're truncating them completely after the second attractive maximum. There's no minimum, there's no long range directions, they're tunable along 2 parameters, so I'll open up 2 two-dimensional phase spaces for those 2 different shapes. Those are just the specific parameters. And keep in mind that those are one-dimensional systems. So for hard matter, that would mean elements, not any compounds. So the simulations are pretty standard again, molecular dynamics this time. Blue is the software that I was talking about. Now we can really perform these simulations in GPUs. They're beautifully fast. We have around 4,000 particles for each simulation, many millions of steps. And all we do really is, as if we were experimentalists, only that we don't get our hands dirty. We start at high temperatures, we have a gas, we cool down, we have a liquid droplet form, we cool down further, the crystal forms, and at some point it's really nice and clean. So that's where the fun happens, because then we have to determine what the structure is. These are the phase diagrams that pop out of this. Of course, it takes forever to analyze these, because this was before we used anything fancy for analyzing the phase space. Basically, we're trying to do a lot of these steps now with some machine learning tools, but honestly, it's not trivial, A, because of the order parameters, but also because you have very different regions of phase space. You have huge regions that are boring. This is all the bi-centered cubic structure that is very simple and very clean and very boring and easy to recognize. So if you go through them frame by frame, that one is easy. You have entire regions that are much more complicated, both in structure, but also with way smaller stability regions. So it's actually not trivial to automatically investigate those. But you can see, hopefully, that some of these colors are the same in both the systems, so some of the structures form irrespective of the specific shape of the interaction potential. And you see that some of them are really close together. Like you have a lot of phase variety in small regions, and that is also mimicking what happens in a lot of intermetallic systems when you have a lot of phase variety in a very small compositional space. These are the crystal structures that we were able to tease out of the data set. Everything that you see on the left are known crystal structures. So this might be too small, but basically I'm giving you the Pearson symbols again, and they shockingly, again, correspond to metals. Maybe not something that shocks you yet, but everything on the right side are new crystal structures. And that's where I was very happy that I had something to do that I was really useful for, because I was still new to simulations when I was doing this work. But what you can see is we have the Pearson symbol, because we can determine the symmetry, we can determine the unit cell where the particles sit, but we don't have a prototypical compound because none such exists. And for a while it was just happy that we could find new things, but then of course we're wondering why. Why do we see structures that nobody has seen before? And it starts making sense if you look at the coordination numbers. So if you if you look at it as a chemist, which I'm not, and I know that some of you are not either. But if you just look at how many nearest neighbors each particle has, you see that, so at the top I'm showing you the particle environments, and at the bottom the crystal structure types. Aligned is by coordination numbers, so up here they're discrete because each particle environment just has an integer number of neighbors. But down here you can have any, these are rational numbers because these are all periodic crystals, but basically you can have any amount of neighbors on average because you can have different environments formed in crystal structure. So on the very left you have 4 nearest neighbors, for example, like you would see in silicates. Anything that's sp3 bonded would have a tetrahedral local environment. And on the right you see high numbers, high coordination numbers, 12 or 14, like sphere packings, like you would see in metals. So that's where our known structures sit. I think the nuance that is probably lost here is that all the ones with the X's, the new structures, are printed in red, and they're almost all here in the middle. And if you still wear your chemist's hat, you'll find, okay, of course, these are one-component systems, and they have nearest neighbor numbers of 9 or 10 or 11, which no atom wants to have. That doesn't fulfill any octet rules, right? Those are just numbers of nearest neighbors that maybe in a compound you would see when you have 2 different components, but not in element structures. So that's where we see the new structure types, where we're just not mimicking actual atomic chemistry, right? The periodic table is discrete. However, for one, that means that our potentials here probably just don't mimic any atoms. That's fine. That is maybe not shocking. what it could also mean is, if you think about particles on the mesoscale and designing structures, the experimentalists are usually trying to target specific structures that they want their nanoparticles and colloids to assemble into, and they think about structures that they know from the atomic scale, because that's the only crystal structures we know of. These could all be design targets for nanoparticles. We don't actually know what their properties are, and I'm definitely not the person who will figure that out, because that's not our expertise in my group. But basically, all of these could have interesting properties, hopefully. I'm still hopeful. That we just don't know about, because we didn't know they could exist as crystal structures. But on the mesoscale, we have all those different design dimensions in which we can change our particle interactions and shapes. And we could hopefully try to really synthesize structures that are clearly possible, but just not with the periodic table of elements. All right.
Do you know where in respective potentials these particles are sitting? I mean, they're not all sitting at minima, are they? Or are they?
That's a really good question. They are mostly sitting at the minima. So that's an excellent question. One of the things that I would want us to at some point be able to do is really map from the shape of the interaction potential to the crystal structure. We cannot do that yet. I assume it's a very high-dimensional, non-trivial problem. So whenever we try to map like just the wells or the well positions, the well depths, it was never that clear a relationship. So there are clearly many factors, and then also we don't, of course, know the entire space of crystal structure. Like I probably didn't see all the ones that are possible either. So they usually sit in the well. So what we've done is we've plotted the radial distribution functions where you have maxima for the interparticle distances in your sample over the potential. So you can really see that they align quite well with one another. All right. So growth is an interesting question here for me. If you think about the complex structures, so let me actually go back 2 slides. Some of these structures are really simple, and they fully fulfill what we think about as crystal growth. We think about crystal growth being one particle coming near a surface and just sitting on its place, and then the next one coming in and replicating the same environment over and over. That's not how most crystals look like, actually. These particles are all identical, but the environments are not the same. So you have sometimes large, this is a unit cell with 16 particles. The environments are all the same, but they have different orientations. So they have to come in and somehow know where exactly to sit. And some of them have different environments. Here, for example, this TP30 structure has 5 different Wyckoff positions. So those are relatively complex structures. And also, if you think about just the unit cell size of 100 particles, that means you have your 101st particle come in and know somehow where it's supposed to sit, even though it cannot see particle number 1, whose crystalline position it's mimicking, right? Somehow, because of the energy landscape that's being built by the already attached particles, the next particle will know where to sit. But it's not as simple a picture as we usually think about, like with the little cubes fitting into the little cube-shaped holes, or like we saw in the nanoparticle case. So basically, we're wondering, if it doesn't look like this, how does growth proceed? And we think that actually these models are pretty neat when it comes to that. They're really simple. We're not templating any specific lattice onto this. We can change which crystal structure's growth we're investigating with just changing the interaction potential by a little bit. So we're taking our isotropic pair potential. This one forms this tetrahedral local environment that assembles into the class-grade crystal structure, which actually, when it comes to the wells and how they align with the neighbors, we'll actually see that all of the low coordinated structures with, for example, 4 nearest neighbors will have this minimum that is not net attractive. And then the second nearest neighbor shell is the one where the attractive minimum sits. Okay, so this is one of the structures that assembles, and we know that it also that is also observed in nanoparticles. These are DNA functionalized nanoparticles that form this exact geometry. So somehow they know where to go, even though they don't have like an IKEA map for what they're supposed to do. And one of the things that comes in here now are, again, order parameters. So if you think about, for example, just being able to, like, wanting to be able to distinguish solid from fluid like we did earlier, or in this case, the cubic from the hexagon, closed sphere clamping. You can do that relatively easily with a low-dimensional order parameter that in this case, it looks at the symmetries locally, it uses spherical harmonics to encode them, and you can tell them apart quite well. However, if you look at more and more complicated structures that are locally more and more similar, you'll actually not be able to tell them apart with something like this. So the order parameter that we're using is way more high-dimensional, and it takes the local environment apart essentially into what does do the 4 nearest, where do the 4 nearest neighbors sit, where do the 5 nearest neighbors sit, and so on. And you're able to suddenly tell those two structures apart way, way better, so up to the point that you can tell apart different class-like structures that locally all look like little tetrahedra and have huge unit cells, but still we'll be able to distinguish them if we use a high-dimensional order parameter and machine learning to evaluate it, because otherwise we can't make sense of this data. So really with that kind of order parameter, we can tell apart these 3 different class-like structure types in this one test data set that had been originally manually investigated and then now this was tested on by one of my colleagues in Michigan. Okay, so we have a way of looking at these structures and the kinds of different types of crystal structures and how they grow. They can differ in their coordination number, right? I already showed you we're kind of spanning the gamut with the system, and in complexity. So we can have really simple ones that have just one local environment, 5 different local environments. It can get more complicated, but we don't have to go there, and it will already be complex enough. So one of the very simple, highly coordinated structures that we're looking at is BCC. So pretty simple sphere-type structure. You can have simple low-coordinated structures and complex low-coordinated structures, the class-rates. I'm not going to confront you with all of those at once. We're just going to look at 2 extreme cases. Many neighbors and few particles in the unit cells, and few neighbors and many particles in the unit cells. So the one at the bottom left is simple. We look at how it assembles in the beginning. We're now applying this order parameter to the simulation. In the beginning, everything is purple. So the number of clusters that we're fitting this to is actually not that easy to figure out, but here, trivially, it's 3 of them. We see a gas form. As the temperature is being lowered, you see that something nucleates. It starts being blue, and then at the core, red particles appear. And we can look at it once more, but basically, at the end, what Maya, my student, has been doing is she's taking away all the particles on the surface. She's cropping those away so that you can look at the core of the particles. So we have the gas, something that's fluid and surface all at once, the blue ones, and then in the bulk you have just red particles. So 3 different environments. If you look at these clusters and the coordination numbers over time and how many of those particles you have, you can see that the gas particles are low coordinated, that makes sense, and they disappear over time. This is where condensation happens, and initially you have just your fluid droplet, and at the very end you have your crystal condensed. So 14 nearest neighbors, that's your BCC structure. And you have some persist at the very end, that's the surface particles. So this is relatively straightforward. What we can do as well is we can do this for the class rate, where we have 5 different crystal positions. So we have to apply a higher number of clusters, and we can still see we have just a gas. We have a droplet form in the gas. But then the crystal that forms has all those different types of positions, all these different, like represented by different colors, that actually occur in a periodic way. So you have the same color pattern in every unit cell. That's because the order parameter is capable of distinguishing the different local environments from one another, different crystalline local environments. And while this is just proving to you that we're capable of doing that, what we actually want to see is how does a particle come in and decide I'm going to be part of that environment or this other environment. Not only are there 5 different ones, so this is the fluid, and then we have 2 0-coordinated and 2 4-coordinated ones. That means that if we map them to the Whitehead positions, we actually have one cluster that encompasses 2 Whitehead positions, but we can change the number of clusters. We can basically tease them apart and have it like be convoluted here once, convoluted there once, and ultimately we're able to assign each particle to its correct position in the lattice. What we can do with this now is say, okay, do they behave differently from one another? Because we have particles not just that are like in slightly different symmetrical positions that are effectively equivalent, but some of those particles are zero coordinated, so they have their first neighbor shells empty and they sit in these huge cages in the clathroid. And the other particles are four coordinated, they form the framework that makes up the clathroid. And they really differ in how they behave once they're part of the crystal. The zero coordinated particles are almost never able, and I don't have plots for this unfortunately, but this is a really recent analysis that my student has done. They don't exchange almost ever with the framework. So you almost never have an exchange of zero coordinated particles with the four coordinated ones as soon as your crystal is condensed, whereas the particles in the framework are diffusing. So they can go back and forth between different micropositions. So basically, as soon as they are part of the crystal, they've adopted an identity, and even though they're physically identical, this identity has repercussions on how they behave in the crystal. They take on two different types of behaviors and they stick with it as soon as they're in the condensed state. That's the kind of insights that we want to gain from these structures, and we've applied these order parameters and this like analysis of their growth behavior to other crystal structures now too, and want to try to tease out how they behave. Some of them are going to be a little less interesting. I expect that for these intermetallic compounds where you have different environments, but they are physically really similar, you're not going to see a lot of distinctive behavior between them, but if we do, I'm going to be happy too. But for the clathroids especially, you have these two very distinct behaviors depending on where your particles end up sitting, even though they're actually identical in their interactions. Okay. I have one more section, but I have two more. I will definitely skip one. Do you want to go one more? Or do we?
We've got questions there. It's easy.
Okay. Yeah. All right. This one, the project that Jasmine is doing, she's our lab's main chemical engineer, so this is actually a really fitting topic, is kind of trying to cater to experimentalists in the sense that whenever I show them these other studies, they're like, oh, what if not all of my particles are identical? Because that's what happens when you synthesize particles. They're slightly different in size or slightly different in shape or whatever. And that's what we want to address with Jasmine's project here, where she's looking specifically right now at BCC structures, so relatively simple structures, and how they react to the introduction of a second size. So you can perform simulations with all kinds of sizes all at once with the size distribution. They're just very expensive because all the particles are suddenly distinct. So what we're doing here is we're disturbing the system with a slightly more simple manipulation, but we're still trying to see how sensitive to different sizes is the system aware. So what we did was we took this Leonard-Jones-Gauss phase diagram. All the pink regions, remember, are BCC, so that's where we're doing our investigations. And we're not just taking one type of particle now, but we're introducing a second size. We're shifting our potential by some amount. So we have the interactions between just the small particles, interactions between just the big particles, and then in between, we have the cross interactions between the big and the small particle. And basically, what happens is stoichiometrically, we're not making our lives very difficult. Those are just 50-50 mixtures, and they assemble into a little droplet like they would if there was just one type of particle. And we're probing these two regions now and checking, well, we have different interaction potentials, all forming the same crystal structure. How do they react to the introduction of a second size particle? So there are actually two quite different regions here. The one on the left is the single well region, so that's when you have your Leonard-Jones and the Gaussian sits essentially on top of it and just slightly distorts the shape of the interaction potential. And what I'm showing you here in the color is the robustness with respect to the introduction of the second size. So this is the terminal size ratio, which means if, okay, one means that they're the same size, so if the structure doesn't form then, we have a problem because then that was never supposed to be BCC in the first place. But if it's like 99%, it means your particles are just a tiny bit different and already the structure formation breaks down. If it's around 92%, you can change your particle shape quite a bit, particle size quite a bit, and your system reliably forms the correct crystal structure. And you see that for the single well region, it's pretty not robust. for most of it just down here, where essentially your Gaussian almost disappears entirely, that's where you have a little bit more robustness. So the breakdown happens very early if you see any dark reds, and you have really high robustness when you see yellows. And in this double well region, where essentially you have your Leonard-Jones potential and your Gaussian added on top of it, but with different depths, you see that you have way more highly robust systems, where your second particle can be quite different in size compared to your first one. Okay. Set all this, so move on. The other aspect of this is not just the double well region is better, but also the breakdown behavior is a little different. The single well region over here, what essentially happens is you have a lot of particles in the correct environment that's supposed to be orange. And then at some point when you change your size ratio, you make your sizes slightly too different, it breaks down and never comes back, and the particles are just disordered. In the double well region, you have more fun stuff happening. So it goes down a bit, and actually the size ratio that's displayed here, that's the most conservative estimate, that's the first step down. So you can see, even as this happens, even at those like about 90%, you still have a sizable chunk of particles in the correct environment, and that's because of what happens locally. So in the single well region, you have, now here you see the two different types of particles highlighted, A and B type, and on the right you see which particles are in the correct structure. If it's yellow, it's BCC, if it's white-ish, it's not, which means after the step down, no particle is in the right environment. Pretty boring. In the double well region, you can already see here that what's happening is that here gradually and here completely, those two sizes demix. And ultimately, you have your correct crystal structure here in full bulk. Here you see that the disorder impinges on the crystal more and more, but ultimately both of them actually crystallize in the correct structure only separately. So if you make these particles, which fortunately you're not in charge of, but other people know how to do, you can actually rely on having way more robustness with respect to you're still getting the structure you're going for, even if they're not all identically sized. That's what we're hoping to do here. And basically, the other Hillary's part I'm not going to be able to talk about, but what we're doing next year is trying to probe different kinds of crystal structures. This is just BCC, but in a previous study from like 10 years ago, actually other researchers have found that you can have gyroid-forming particles that as you change size dispersity, as you increase size dispersity, stability increases, so you can stabilize crystal structures with size dispersity. And we're hoping to see that maybe some of the crystal structures are more robust, not just slightly robust, but actually are going to embrace the size dispersity that we're going to introduce. Let me skip this last bit. Hillary found more different crystal structures, which I hope you'll believe me. But just to wrap up real quick, I hope I can show you that hard colloquium do fun things. They assemble crystal structures and show all kinds of different structural behaviors that you might know from atoms, but not from hard colloquium. We looked at some size effects and confinement effects. And then in our squishy spheres, we found all kinds of crystal structures, and we're trying to use them to probe how do those particles grow, hopefully with repercussions to actual atoms or nanoparticles, but that is of course just fantasy for now. And in another sense, what happens if you disturb your system, for example, with respect to the size, dispersity, or lack thereof. So some of the things that I showed, especially initially, were done in the group where I did my postdoc with Sharon Glotzer. This is one of our Zoom group pictures. We don't have a real life one yet, but we're working on it. This is my wonderful group, and I showed you for most of my PhD students what they're doing. Thank you so much again for your invitation, and I'm happily available for more questions if you have any.
So we have a few minutes for questions.
Hey, thank you so much for the talk. I was wondering if you could kind of talk about some of the significant computational challenges that you face in these simulations and what your group might be doing to address those challenges.
That's a really good point. One of them is, for example, when it comes to size dispersity, right? We are just probing what happens if you introduce a second size, not if you have a real distribution, because that's way more challenging. One thing we actually want to do is one of my former colleagues, now collaborators, Chrissy Du, who's now at Harvard as a postdoc, she is working with people at Google Brain to develop an MD, or it's already there. They're developing an MD algorithm that is actually a little slower than HUMD, but because it inherently treats each particle as like non-interchangeable, each particle is already distinguishable. I hope we can use that to attack Pauli dispersity, to actually have a distribution of sizes, where right now we're just like using kind of a crutch to mimic the behavior at least a little bit. But that's not our, like, we're actually not developers in that group. So most of the students that I'm working with, some of them have, like, most of them have coded before, almost none of them had simulated before. So we're really using the code as is and then trying to set up new experiments. Really what we do are computational experiments way more than any kind of theory. Yeah, so we're not redeveloping new codes, we're trying to use the codes that already exist in a way. And that's also true when we ever say anything about machine learning. None of this is fancy new stuff, it's like scikit learning, essentially, that we're employing, and usually with help.
Thank you.
So you mentioned that like these double well potentials are like good models for like certain materials like copper or something. Is it, so, and then you made this phase diagram. Is it possible to go the other way around and like say, I have potential, let me make a material that like mimics that potential? Is that like an addressable problem?
That's a good question. Basically, my hope is that on the nanoscale, that's what we can effectively do. Where we are, with potential, we're just prescribing this is where the wells sit. So this is where your particles want to sit. Effectively, if you have a faceted particle and it has two different types of facets, your neighboring particles can sit at two different types of distances, for example. Or if you have something like what we call a micelle, and like it has a squishier outside than inside, then you have like two characteristic, we talked about this so much, two characteristic distances at which your neighboring particles can sit. So we haven't done this rigorously. This is all very kind of wavy. When I say it like this is about the depth to which we've gone. And there are people who are in the business of doing it like the way around, where they say we have this particle, how can we express it through a potential? People don't usually go back. But I think we need to explain that what we're doing is relevant. So I think that for the multi-well potentials, the ones that don't have the repulsive clump in between, I think we can make a case that that mimics the kind of behavior where you really have two attractive wells and distances that are relevant to a particle. If you have a repulsive clump in between, I think it's a little harder to make that case, and that's more where we're really mimicking hard matter behavior. And there, because we're just screening the entire phase space, we're not really saying this is for aluminum works and this is for copper works in, right? We can't, unfortunately. But yeah, we're kind of reverse, we're going from the reverse. We're saying what would even be possible, and then hopefully later we'll be able to address, well, how can you actually? Yeah, it's not something, we're really trying to go the other way, but it's not something that's like already established.
Okay, thank Julie again.